So in this video we'll try to implement the quicksort algorithm. We already implemented the bubble sort, insertion sort and selection sort algorithms. Now here we'll be trying to implement the quicksort algorithm, and after this quicksort algorithm we'll see that merge sort algorithm, and then we are going to compare these algorithms on the basis of time complexities. Okay, so what is quicksort algorithm? That we have already seen. Given an array like this, assuming that this is an array, now here in this array we are going to have some elements, assuming elements are 4, 0, 1, 9, 11, 6 and 5. Now on this array, first of all we are going to apply the partitioning algorithm every time. Okay, so quicksort algorithm uses the help of the partitioning algorithm, and that partitioning algorithm we have already seen. So what is the quicksort algorithm? We are going to say quicksort on array A, where the starting index location is P and the ending index location is R. For example, here the starting index location is P and the ending index location is R. But you have to keep in mind that when we are implementing these programs, so during program implementation, the starting index locations generally they start from 0, and when we write algorithms, then the index locations generally start from 1. So here we have 0, 1, 2, 3, 4, 5, 6 and so on. These are the index locations that we will be having, and the value of P and R, it is going to change during the execution of the programs. So quicksort algorithm is something like this: quicksort on APR, then it is if P is less than R, then we first of all we do partitioning on this array A. So we do Q is equal to partition APR APR, and then we again apply quicksort on the left side of this queue and on the right side of this queue. So we are going to apply quicksort on A P Q minus 1, that is on the left side, and quicksort on A Q plus 1 to R, because the element which is present at the qth index location, that is present at its correct location. Okay, that is a quicksort algorithm. Now the major thing, because see you can clearly see here in quicksort algorithm, in these two cases we are using recursive programming, and I hope that I've already explained you quicksort algorithm very well in the preliminary course. So here in this case you can see these two are the recursive calls, and this is the partitioning procedure. So one of the major portion for implementing the quicksort algorithm is to implement the partitioning procedure very well. If you can implement the partitioning procedure well, then you can easily implement the quicksort procedure. So first of all we have to implement the partitioning procedure, and after implementing the partitioning procedure we are going to implement this quicksort function. Okay, so let us take this step by step. So initially we'll try to implement the partitioning procedure. In partitioning, so what is the partitioning procedure? In partitioning we take a pivot element. Okay, so for example, if this is an array which is having some index locations, because in partitioning procedure we are going to pass the starting and the ending index location of this given array. So assuming that first index location is P, this one will be P plus 1, this one will be P plus 2, up to so on. The last index location will be R. Okay, so what we do is we call partitioning on this. So we call partitioning on A P to R. So what is this partitioning procedure? In the partitioning procedure we are going to take a pivot element. You can take any element as pivot if it is a randomized quicksort, or either you can take the beginning as an element as a pivot, or you can take the ending element as a pivot. That is your personal choice. So assuming that I'm taking the last element as pivot, because that one is the easiest to understand as well as the easiest to implement. So we'll be taking two pointers here. Number one pointer is I and second pointer is J, and this pointer I will be pointing to one location less than J. So we are going to increment J every time, and if the element present at this location, if this element is less than or equal to the pivot element, then I'm going to increment the value of I, and then I'm going to swap the values of I and J. Just for simplicity, let us assuming that we are having some elements here. So let us assume that we are having the elements which are 5, 4, 0, 11, 62, 7, and here we have the element which is 3. Now you can see the pivot element is having the value which is 3. So we are going to compare this value with the j. So this 5 is compared with 3. So you can see 5 is greater than 3, so we are not going to do anything. We are just going to increment the value of j. Now this 4 is greater than 3, so again we are not going to do anything. So we are just going to increment the value of j. Again 0 is less than 3. Whenever this value is less than 3, then we have to increment the value of I, and then we have to swap the values which are pointed by I and j. So 0 will come here and 5 will come here, and then you have to increment the value of j again. Every time you are going to increment the value of j. Again 11 is greater than 3, so there is no problem. Again increment the value of j. 62 is greater than 3, there is no problem. Again increment the value of j. 7 is greater than 3, there is no problem. Again increment the value of j. Now 3 is not greater than 3. Actually this is 3 is less than or equal to 3, right? So either you can implement it like this, that j, if j and pivot both point to the same location, or there is one more way of implementing is you can just say if the value pointed by j is less than or equal to the pivot element, and you can say 3 is less than or equal to 3, therefore I'm going to increment the value of I and I'm going to swap it. Therefore 3 will come here and 4 will come here. So after this entire partitioning procedure, what is the content of this array? The array is containing 0, 3, 5, 11, 62, 7 and 4. These are the contents of this particular array. And you can see the pivot element, whatever the pivot element was. For example, here 3 was the pivot element. Now all the elements which will be in the left of 3, they will be less than or equal to 3, and all the elements to the right of 3, they will be greater than 3. Okay, and why I'm keeping it less than or equal to 3? Because I wanted to make this algorithm as a stable sorting algorithm, right? So I think you already understand what is a stable sorting algorithm or what is an unstable sorting algorithm. So we are going to implement this algorithm here, this partitioning procedure, and we are going to use this partitioning procedure in the quicksort algorithm. So let us take it step by step. So we will be having a partitioning procedure initially. So we are going to write program for partitioning procedure, and this partitioning procedure should return the value of the last location. For example, here it got 3, the value of 3, or you can say the last value of I is the I is pointing to this p plus 1 index location, so it should return the value of that index location. Therefore the return value of this partitioning procedure will be integer. So I'm going to write integer partitioning. So let us assume partition for simplicity. I'm going to take an array A. So I'm going to take integer A. This is the array A, and I'm going to take the first index location, that is P, and I'm going to take the last index location, that is R. So we are having 2 index locations which are P and R. Now here in the partitioning procedure, I have to take 2 values. Okay, these are not exactly pointers, these are remembering the index locations. Therefore for I and j we can take some integer values, as well as for pivot also we are going to take some integer values, because pivot is just going to point to the last index location, so we just have to store that particular index location. So I'm going to take 3 pointers, which is I, integer I, comma j, comma pivot. Okay, and here I'm going to make I is equal to -1 or minus p minus 1, because I have to make I to point to one location less than p, and then j is equal to p, or j should start from p, but we can take j in a while loop or any kind of loop, and we are going to make pivot to point to r. Okay, now I'm going to take a while loop here, so or make it a for loop for j is equal to p and j is less than or equal to r, and we are going to increment j plus plus. That means j should be incremented every time. So every time whenever you are going to increment j, so you have to check whether the value pointed by j is less than or equal to pivot or not. So if a of j is less than or equal to the value which is pivot, then or some people actually call it as pivot. I prefer calling it as pivot. Then I have to increment the value of I, and then I'm going to swap the values of I and j. Okay, so I'm just going to swap the values of a of I, and so for a of I I'm going to represent a of I, a plus I, and a plus I, a plus I and j. So we are going to swap the values of I and j. So again we have to implement this swap function. Okay, so after this entire for loop we have to return the last value of I. So this is the partitioning procedure. Okay, remember that we have to implement this swap function, so I'm just writing it here. The function name will be swap. Now this function should take 2 pointers as input because it is a call by reference function. So swap int star I comma integer star j, and then it is going to take integer temporary variable. So integer temp is equal to star I. Actually I don't have to implement the swap function separately, but let us just assume I've implemented it here. So I have to make star I is equal to star j and star j is equal to temp. So this is how we implemented the swap function. Now this partitioning procedure is done, swapping function is done. Now we just have to create a function to implement the quicksort. So the function name will be, assuming it is quicksort, on integer array A, and starting index location will be P, ending index location will be R. So we are just going to say this: if P is less than R, then we have to do integer Q is equal to partition A comma P comma R, and then again we are going to call the quicksort on the left side of the array as well as on the right side of the array. So we are going to call quicksort on A, P, Q minus 1 as well as quicksort on A. So I forgot this bracket here. So quicksort A, Q plus 1 comma R. And this is how we implemented the quicksort function. As you can see, it is very easy to implement, and I just confirmed that all the brackets are okay. So now we are just going to try this quicksort function. Let us see if it is going to work or not. So for that purposes I'm just going to take a dummy array which is having 10 values. So this is a dummy array which is having 10 values, and assuming these values are 9, 7, 8, 6, 3, 4, 5, 2, 1, or make it 2, 0, 0, 1. So how many values are there? Let me count it out. So this is 3, 4, 5, 6, 7, 8, 9, 10. So there are total 10 values. Okay. Now we are going to call this function here. So we are going to call quicksort on this array A. Starting index location is 0. Ending index location is 9, and then I'm just going to write a function for loop to print these values. That is for integer I is equal to 0. Then I'm going to write printf, or make it I less than 10, and here I'll be having printf %d space will be having comma a of I plus plus. So this is just a simple printf function. So we are just going to print these values. So let us run this function. So we'll be having build and debug, and let us see if there is a so there's an error in the program. So let us first of all identify where is that error. So maybe we have missed some bracket. So it is saying that we missed something. So you can clearly see here in this line we missed an equal to sign. So after this equal to sign, and they are saying this okay, fine. So let us see if it is working perfectly or not. I'm again going to try build and run. You can see it is working like this, and it is just printing the same array, and it is not returning these values. So let us figure out what is the issue here. So we are having 9, 7, 8, 6, 3, 4, 5, 2, 0, 1. So we are printing exactly the same array. So do we have any problems in this program? Let us see that. So partition on APR, so it is also taking that array, it is also taking that array, and quicksort on A. Okay, so 0 to 9. So I'm calling this quicksort function here, and this is the array. I'm calling this quicksort function. So here in this function I'm just passing this array here, and I'm passing the value of P and R. And okay, so let us do one thing. Let us take this integer q instead of here to here. So I'm just going to take integer q. Now let's see if it is working correctly or not. So again, try build and run. It is not working. So it's not making any changes. Where is the issue? Just figure out the issue once. So here it is. Here we have the swap function. Is it working correctly? The swap function. So we want to swap these values. I think it should work correctly. Is this P to R, and then every time I'm going to do J plus plus. If A of J is less than equal to pivot. Okay, so here is the problem. So here we have to do the initial value of pivot is, so here A of J is less than equal to A of pivot. This is the problem. Actually it was not the problem, so this is the problem. So we identified the problem. Now let us see build and run. Okay, now it started. There's issues with this, so maybe the program is crashing, so maybe it will be having some issues. Have you allocated some value to pivot? We have allocated a value of pivot, and I'm just going to say if A of J is less than or equal to A of pivot, then we are going to do this. Okay, and this is R. I'm going to increment the value of I, and I'm going to swap the values A of I and A of J. Okay, and then I'm going to return the value of I. So any issues with this? A of I plus plus, from 0 to 9 I'm printing these values. No problems here, no problems here. So Q minus 1, so if P is less than R, then only we are going to do this. This is also correct. So maybe we are missing some statement here, so we'll just try it again. Okay, so fine. So I think I got the issues. The problem is with the return statement, because I think so this return statement is inside this for loop, and we should not have returned this return statement inside the for loop. It should be outside the for loop. So here we have this problem, and if you try again build and run, you can see it is working perfectly. The major problem was because we have returned this return statement inside that curly brackets. So you can see here it's so simple, guys. It's so simple to implement. Now let us first of all identify this quicksort algorithm, and we'll try to compare it with the other algorithms. So let us first of all identify how much time it is going to take. Here in this program we have already implemented the other function so I'm just going to copy this code for the quicksort function with the last code that we implemented. So instead of cut, I just do copy. So there is Control plus C. I'm just going to copy this one, and here I'm going to implement it. So after this is improved bubble sort, and here, so the old program itself. So I'm just going to copy option. This is Control plus V, yeah. So it is pasted here, and now we are just going to copy this program for quicksort. So this is we already implemented. So again, this is the initialize array. Now this, in this case, I'm going to call QS quicksort. So we are going to call QS on ARR with starting index location as 0 and ending index location as 9999, because the size is very good, very huge. And millisecond for the quicksort function. Now let us compare these values for here you can see the quicksort function should behave first, because here the data is already sorted for this array, right? So we have already sorted data. So I'm just trying to build and run, Now let us see, it is showing that for insertion sort function it is taking 155 milliseconds. For improved bubble sort function it is taking 313 milliseconds. For selection sort function it is taking 130 milliseconds, and for quick sort function it is taking 244 milliseconds. Okay, and every time inside this array we are having these values, but better than this we can have we have a random values. So to use the random values we have to use a function which is rand function, and this rand function is already available for the C language and C++, and even Java you can find that random function. So I don't know if there's any header file I have to implement, so let us try to see rand function. Yeah, let's try to see if we can find a rand function. So yeah, so we have a rand function which we can call. Let us see if I can have a different time with random values, because we know that quicksort function behave the worst if we have the sorted data, either it is sorted in increasing order or decreasing order, but it behaves better if we have an unsorted data. So here we are just going to have a random function which is going to generate random values. Now because of this random function, now you can see quicksort function is way better than any other function. You can see insertion sort function is taking 80 milliseconds, improved bubble sort function is taking 328 milliseconds, and selection sort function is having 136 milliseconds, and this quick sort function is taking 2 milliseconds. Now this one issues with this one. The issue is that using these random functions, this is random function is generating all the values randomly, so all the arrays will be having random values. Okay, and even they will not be having the same values. So we are comparing all these different algorithms with different values actually, but they are random values, so you can be sure about the random values. So you can see you got this code where we implemented the insertion sort function, where we implemented a selection sort function, where we implemented the improved bubble sort function, then we have the quick sort function, and after this quick sort function we called all these functions with the random values initialized with the array, and after getting those random values we try to find what will be the time taken by this function to sort that particular array. Now next time again if we try to run here, so you can see the quicksort function is behaving the best out of any other function. Okay, so quicksort function is going to behave the worst if we have the data which is sorted in decreasing order or sorted in increasing order, because that's the worst case for the quicksort function. I think you already know why it is a worst case. Okay, so I hope this tutorial is very helpful for you. Now in the next video we'll try to implement the merge sort function. Okay, so let us implement the merge sort functions after this. Thank you.